So I will speak about rainbow fractional matchings. And this is joint work with Rona Haroni and Zilin Jiang. So I will start with rainbow matchings, and fractional will come later. So to give you an idea of what is a rainbow matching, suppose you have 8 vertices, and here is a matching of those 8 vertices. So you should imagine that this is matched to this, this to this, this to this, and this to this. Here is another matching of those 8 vertices. Here is yet another matching of those 8 vertices. So it's the same 8 vertices. You should imagine those as on top of each other. And here's yet another matching of those 8 vertices. And now what we would like to do is to choose one edge from each of these matchings. So I colored them by different colors, so I will have one edge of each color, so that the chosen edges themselves form a matching. So we can do that in this example. For example, we can choose this edge from here, this edge from here, this edge from here, and this edge from here. And they form a matching with edges of distinct colors. So this is the idea of a rainbow matching. Now in this example, I wanted an edge from each of them. But in general, we might be able to form a matching using edges from some of them and not using edges from others. So here's the general definition. So given a family M1 up to MM of matchings in a graph G, a rainbow matching is a choice of edges from distinct matchings forming a matching. And here's a theorem which is usually referred to as Driscoll's theorem from 1998, although Driscoll was interested in this question because of some questions on Latin squares. And so he formulated it in terms of Latin squares and not in terms of rainbow matchings. And he also had an additional condition, which later turns out to be not necessary. So in this form, this was reproved by Aharoni and Berger in 2009. And the theorem says that any family of 2n minus 1 matchings of size n in a bipartite graph has a rainbow matching.
When you say size n, what does that mean?
So each of the matchings in the family has n edges.
And there's 2n vertices in the graph?
Not necessarily. Actually, this was the case Driscoll considered, but the graph may have more than 2n vertices. There's no restriction. And we want the same n here and the same n for the rainbow matching that we are forming has a rainbow matching of size n. So we are not going to use all of the 2n minus 1 matchings, obviously. We will use n of them. From each one of those n, we will choose an edge so that these n chosen edges will form a matching. And now I'll show you that 2n minus 1 is best possible. We really need that many matchings to allow us the freedom to conclude the existence of a rainbow matching of size n. So 2n minus 1 is best possible. So for this, we let the graph be a cycle on 2n vertices. And I'll draw here an example of a cycle on 8 vertices. Now, this cycle has 2 perfect matchings. I drew in blue one of them, and I'll draw in red the other. And for our example, we take n minus 1 copies of each of the 2 perfect matchings. So we have altogether 2n minus 2, so one less than this number, matchings of size n. And it's easy to see that there is no rainbow matching of size n, because any matching of size n in this graph must be either the red one or the blue one. So if I could find such a rainbow matching, I would have to choose n edges from the n minus 1 copies of that matching. So I would necessarily have to choose 2 of them from the same copy, which is not allowed by the rules of rainbow matching. Now I should mention that this theorem, which, as I said, started from the study of Latin squares, turned out to have quite a few applications and quite a few different proofs. In particular, Noga alone observed connections between this theorem and additive number theory, and he gave a very nice proof of the well-known Erdős-Ginzburg-Ziev theorem in additive number theory as an easy corollary of Driscoll's theorem.
What is that theorem?
Erdős-Ginzburg-Ziev says that if you give me 2n minus 1 integers, then I can always find n of them whose sum is divisible by n. Yes, and the example that shows that you need 2n minus 1 is very similar. And actually, Aharoni, Kotler, and Ziv proved that for both Driscoll's theorem and for Erdős-Ginzburg-Ziev, this is the only example. OK, so this is for bipartite graphs. And now a natural question is, what happens if you don't assume that the graph is bipartite? And first, I'll show you an example that indicates that this theorem, as it is, does not remain true if the graph is not bipartite. If G is non-bipartite, we can add a matching assuming n is even. So again, I'll illustrate it here. So I take the 2n minus 2 perfect matchings that we had here, and now I add one more perfect matching, which is the following. So every 4 consecutive vertices on the cycle of length divisible by 4, that's why I need n is even, are matched like this. And now I'll convince you that even after adding this further matching, there is no rainbow matching. And the reason is that obviously, if I could find a rainbow matching, I would have to use the new matching, because the old ones didn't have one. So I would have to choose a yellow edge. And let's say, without loss of generality, that I choose this edge. But then this vertex is dead, because the other edges in the rainbow matching must be either from the red or the blue matchings. And none of these two edges can be used, because these two vertices are already spoken for. So at least if n is even, we must have at least 2n matchings in order to get the same conclusion to work. And this is the conjecture. Any family of 2n matchings of size n in any graph has a rainbow matching of size n. So the history of this conjecture is that the example that I gave here was discovered in a paper by Barat, Jarfash, and Sarkozy in 2017. And they didn't dare conjecture that it is optimal or it is extremal, but Rona Haroni conjectured this. And the conjecture appears in print in a paper by him, Berger, Chudnovsky, Howard, and Seymour, in which they prove a weaker result. So this is what is known, saying that 3n minus 2 matchings suffice. So this is Ronnie, Berger, Chudnovsky, Howard, and Seymour that appeared this year. So we have a gap here between what people could prove and what is conjectured. And in this state of affairs, it is natural to consider the analogous question for fractional matchings. because fractional matchings, due to linear programming, tend to behave more nicely than matchings. So here's a quick reminder of what are fractional matchings. So let E be a set of edges. A fractional matching is a function f from this set of edges into the non-negative reals such that for every vertex v in the ground set over which our edges live, if you sum the values of the function on the edges containing this vertex v, it does not exceed 1. So this is a relaxation of the matching concept, because if you take the indicator function of a matching, which assumes a value 1 for an edge in the matching and 0 for an edge out of the matching, then this just says that for every vertex there is at most one edge in the matching containing it, which is the definition of a matching. And the size of f is the total sum over all edges in E of the values of fe. Again, this agrees with the notion of size for an integral matching. And we are interested in fractional matchings of the largest size. And their size is called the fractional matching number and denoted by nu star of E. Nu is the usual notation for the matching number. And this is fractional matching number is the maximal size of a fractional matching for E. And in bipartite graphs, due to Koenig's well-known theorem, we don't gain anything by fractionalizing. Any fractional matching contains a matching of the same size. But in general, mu star E may be larger. And the most simple example is a triangle graph where you can give weight of 1/2 to each edge. And this gives you a fractional matching of size 3/2, whereas you don't have a matching of size more than 1 in this graph. And is always an integer or half integer. Half integer, I mean an integer and a half. Like in this example. OK, so this was a quick reminder.
Is 3/2 the best you can do?
In this example,
the ratio in general, is it the biggest possible ratio between the fractional matching and matching number, or not?
for graphs? Yes. So here's a theorem that we proved. Or let me first give a definition of what is a rainbow fractional matching. So given a family of E1 up to EM of sets of edges in a graph G, a rainbow fractional matching is a choice of edges EI in the set EI together with a function or a fractional matching f from the set of chosen edges into the non-negative reals. So again, you have a given family of m sets of edges. Each of them you could think of as a color class. And now you want to choose one from each, or at most one. That's the same thing, because you can always add 0 values here, in such a way that for the chosen edges, you can find a large fractional matching. And here's the theorem that we proved. Any family of 2n, any family E1 up to E2n of sets of edges in an arbitrary graph G with fractional matching number of each of them being at least n, I from 1 to 2n, has a fractional rainbow matching of size n. So I will write something additional, but what I wrote so far is the fractional version of the conjecture above. The same 2n, but now both the assumption and the conclusion having to do with the number n is now about fractional matchings. So each of them is not assumed to be a matching, but it is assumed to have some fractional matching of size at least n. And the rainbow choice is concluded to exist having also a rainbow fractional matching of size n. Note that there is no connection between the values of the fractional matchings on the edges. We are not committed to the values. We can use any values we want, but we are committed to the choice of edges.
Is there a relationship? Like, can you deduce the known theorem from this theorem?
No. Unfortunately, no, because
there's a 3n and a 2n that I thought are somehow like this 3 halves thing.
So, well, in this ABCHS paper, I mean, you know, is there a stronger statement they prove for which 3n minus 2
Sorry?
actually? So in this 2019 paper by
Yeah.
Is there a stronger statement they prove for which 3n minus 2 is actually tight or something like that?
No. It's still conjectured to be 2n, the answer.
No, but like, is there a stronger version of, if you add extra hypotheses, then is 3n minus 2 the right answer or something like this?
I can say one thing. I will mention later when I get to the proof of our theorem. Briefly, I won't actually present the proof. You will see that it uses a topological theorem that requires some topological property. If I have time, I will at least say what the property is. And it is known that that topological property does not hold for anything better than 3n minus 2. So in a sense, it is best possible, the best possible result that can be proved by the topological method. Now, I will add to this one more thing. If G is bipartite, then 2n minus 1 sets suffice. So the same proof with a minor modification shows that if G is bipartite, then 2n minus 1 sets suffice. And this part of the result recovers this theorem, because in bipartite graphs, there is no difference between the fractional and the integral matching numbers. And therefore, the second part here is equivalent to Driscoll's theorem. And actually provides a new proof of it via fractional matchings. And I think it provides an insight that actually Driscoll's theorem is about fractional matchings. For fractional matchings, it holds whether or not the graph is bipartite in the appropriate form. And the reason that we don't know the exact answer for non-bipartite graphs, and this is only a conjecture and there is a gap, is that in non-bipartite graphs, matchings behave differently than fractional matchings. And so we need other tools to handle matchings in general graphs. Yes?
So, just to understand, the same example would tell us that 2n is best possible for general graphs?
Yes, it will tell us, although there are simple examples for that. But in this example, it is still true that 2n is best possible even for fractional matchings. And even if you assume that the given families of sets actually have matchings of size n. So even if you do go as much in your own favor as you want, and you assume matchings for the condition, and only require fractional matchings for the conclusion, you still cannot do better than 2n. Now, I want to give a more general statement of this theorem, which is really the form in which we proved it. And the generalization here will be to pass from graphs to hypergraphs. So again, a reminder. In an R uniform hypergraph, edges have size R. So a graph is a two-uniform hypergraph. And it is R-partite. This is the analog of bipartite for graphs. If the vertices are partitioned into sets V1 up to VR, so that every edge has one vertex in each VI. And fractional matchings are defined similarly so I could just repeat the same definition, but now you should think of edges as R tuples rather than pairs. But now the fractional matching number, you might naively believe that because in graphs the denominator has to be either 1 or 2, an integer or a half integer, then perhaps in 3 uniform hypergraphs it must be either 1 or 2 or 3. Well, this is not the case. It can be anything. So now nu star E may have arbitrary denominators.
And also the gap is arbitrary?
And also the gap can be larger.
Not very.
Hmm?
Most uniformity minus something.
Yes.
Yeah, and it cannot be
More than the uniformity.
So I mention this because you see here n could be an integer or a half integer. That these are the only relevant cases. And 2n is an integer even if n is a half integer. But in the theorem that I will formulate now, this is no longer the case, so we have to take to round it up. So here is the theorem. Let r greater or equal to be an integer and n be a positive rational number. This will be the assumed and required size of a fractional matching. Any family E1 up to E r times n, this is the generalization of 2n. But as I said, this may not be an integer, so we round it up. Of sets of edges in an R uniform hypergraph H with fractional matching number of each of them being at least n, I goes from 1 to Rn rounded up. Has a rainbow fractional matching of size n. And the second part, again, corresponds to the counterpart of bipartite graphs, which are r-partite hypergraphs. If H is r-partite, then r times n rounded up minus r plus 1 sets suffice. So if you take here r equals 2, and then the relevant values of n are integers, because these are fractional matchings in bipartite graphs, then you get here 2n minus 2 plus 1, which is 2n minus 1, again, the same number from Driscoll's theorem. This is tight. I don't have examples of tightness for every r and n, but for infinitely many values of r and n, there are examples of tightness.
Can it be projective planes?
Yes, something derived from projective planes serves as an example of tightness.
Oh, cool.
Um,
Another question. In bipartite hypergraphs, it's not true that fractional matchings are matchings, or is it? Like, there is no such correspondence?
No, no. So, indeed, for r equals 2, for graphs, there is a gap in graphs, general graphs, compared to bipartite graphs. But still, the situations are pretty well comparable. When r becomes higher than 2, then we still get the expected and essentially best possible results for the fractional version. But the integral version for r greater than 2 is very differently. So there are examples found by Aaronian-Berger and later improved by Noga alone, which show that if we look at the same problem for integral rainbow matchings, then the number that we need to take here must be exponential in R, which is clearly not the case here.
And even for r-partite?
Even for r-partite, yes. So do I have a few more minutes? Or?
Yes, sure. Absolutely.
OK. So if I have a few more minutes, I will say a few words about the proof. So if we wanted to prove only this theorem about graphs, then we could use the fact that the structure of fractional matchings in graphs is well understood. Essentially, you can take either disjoint edges, or you can take odd cycles with weight 1/2 for every edge. And we could find a proof in terms of standard, or more or less standard, augmenting path arguments. But this breaks down completely for hypergraphs, because there the structure of fractional matchings is arbitrary. And what comes to our rescue in the general case of hypergraphs is topology. And the main tool from topology that we use is the following theorem of Kalai and Meshulam from 2005. Now, their theorem is actually more general than what I will state here. Their theorem is about a simplicial complex and a matroid on the same ground set. But the main case, which also motivated them and is useful for us, is the case where the matroid is a partition matroid. And I will state the theorem for this special case. It will be easier to visualize. So let X be a simplicial complex on a vertex set V. By this I mean a collection of subsets of V that is closed with respect to taking subsets. Which is, and this is the key topological property, D-Lie. And D-Lie-ness is a homological property of the complex, saying that both the complex itself and any induced subcomplex has trivial homology in dimensions d and above. So if you know what that is, then I reminded you of this. Otherwise, I won't go into this anymore. I will just say that the reason, or the background to what Kalai and Meshulam did, and the reason they used D-Lie-ness, is the fact that if the vertices represent convex sets in Rd, and a bunch of them is a set in X, if they all have a common point, then this complex is known to be D-Lie.
This is homology with real coefficients, or which homology?
It's the integral homology with integer coefficients. So this example underlies Helly's theorem for intersections of convex sets. And there is a theorem of Lovász, which is referred to as the colorful Helly theorem, which says that if you have families of convex sets in Rd, and you have d plus 1 of them, and each one of them has empty intersection, then you can also choose one set from each family so that the chosen sets have empty intersection. And this is the application and that Kalai and Meshulam had in mind. Let V1 up to V d plus 1 be a partition of V of the ground set. Assume that Vi is not in the complex. So in the example that I just described, being in a complex in the complex means having a common point. So not in the complex means that they have empty intersection, those convex sets in each of the Vi. Then one can choose Vi in Vi, or I from 1 to d plus 1, such that V1 up to V d plus 1 is not in the complex. So if you understood what I said before, then this theorem gives you directly Lovas's colorful Helly theorem. And this was the main motivation of Kalai and Meshulam. And now we wanted to apply this theorem in our setting. So we can take, I will just describe this without writing. So we can take the ground set V to be the set of edges in our sets of edges. So all the edges that appear, this will be the ground set. And actually, we have a need to do something, a trick that labels each edge by the family from which it arrived, so that we will get a partition. But that's a small technical detail. And this gives us a partition of the set of edges at hand. And the simplicial complex will have as complexes those sets of edges for which the fractional matching number is smaller than n. And then, if we assume that each of them has fractional matching number at least n, then each Vi is not in our complex. And by the theorem, we can choose edges from distinct sets so that they will form a set which is also not in the complex, meaning that it has fractional matching number at least n, which is what we wanted. Very easy, except for the main thing, which is this. So as soon as we prove that our complex is D Leray, then we get our theorem for D plus 1. So what remains to be done, and this is actually the bulk of the work in the paper, is to prove that the simplicial complex that I described has the right Leray property, which is Leray with parameter 1 less than the statement of the theorem, both in the general case and in the R-parted case. And this is this required quite some work. But you have here a method that can be used in problems similar to these. And now I'll come back to your earlier question, and with this I will end, that if instead of the complex in which the simplices are those sets with fractional matching number less than n, which is what I just said, you take those which have matching number less than n in the hope of getting the conjectured result with 2n, then this can be shown, examples exist where this is not 3n minus 4 Leray. And therefore, the best you can hope for is to show that it is 3n minus 3 Leray, which would give the result with 3n minus 2.
And you think it's indeed 3n minus 3 Leray?
There were some reports that people proved that it is indeed always 3n minus 3 Leray, but I'm not sure if this has been checked.
That would reprove that.
That would reprove the theorem of the 5 authors.
So they use some different methods.
Sorry?
They used some other.
They used the essentially augmenting path.
You can tell from the names of the authors. No, you can't always tell, but you can guess, right? They're structural graph theorists, so.
Well, I wrote these notes.
Okay, that, yeah, sure.
Thank you.